The dream or the nightmare of a fixed link between England and the continent has inspired or terrified men for at least 200 years. This illustration showed how Napoleon's armies might invade England by balloon, ship and undersea tunnel. The first crossing of the Channel by balloon had been made in 1785. This design for a tunnel ventilated by iron chimneys was proposed by Walter Mathieu, a mining engineer from northern France, in 1802. Hector Auro's scheme for a tunnel in a submerged tube connecting floating pagodas anchored to the seabed dated from 1851. In 1881, a tunnel some 2,000 yards long was driven out to sea from Shakespeare Cliff near Folkestone in a scheme promoted by Sir Edward Watkin, the railway magnate. It was known as the Beaumont Tunnel, as it was constructed using the Beaumont English tunnelling machine. Work halted in 1882 because of political and military considerations. It was only as late as 1955 that the British government announced they no longer considered the tunnel under the Channel a strategic threat. Another trial bore was made in the early 1920s using tunnelling technology developed by Douglas Whittaker, a Leicester engineer. This tunnel was driven underland at Folkestone Warren. In 1974, construction work started on a joint Anglo-French project, but after a year, the British government pulled out, pleading financial difficulties. Part of the 1974 tunnel was revealed when work on the Eurotunnel scheme got underway. After the UK government pulled out of the 1970s project to build the tunnel, planning work restarted in 1981. And in 1986, President Mitterrand and Mrs. Thatcher gave the go-ahead to the scheme promoted by Eurotunnel for twin rail tunnels. Eurotunnel in turn awarded the construction contract to a consortium of British and French companies known as Transmanche Link, TML. The Channel Tunnel, the land link between Britain and the continent, was at last to become a reality. Two single-bore rail tunnels were constructed, each 50 kilometres long. They are linked to a smaller service tunnel running between them, which is used for maintenance, ventilation, and in case of an emergency, to evacuate the main tunnels. Work began in July 1987 from construction sites on both sides of the Channel, at Shakespeare Cliff between Folkestone and Dover, and at Sangatte near Calais. In all, 11 tunnel boring machines, or TBMs, were required. Here the components which made up a TBM are being lowered down the shaft at Sangatte. A TBM cost about £8.5 million and weighed about 1,500 tons. It took 3 months to assemble, test and commission one of these machines before it could be set to work tunnelling. Once ready, each TBM worked around the clock, tunnelling day and night. The circular cutting head in front of each TBM worked like a giant grater. The head rotated at 2 to 3 revolutions per minute. Working at their maximum speed, each TBM could bore over 400 metres per week. When the chalk spoil was removed, the tunnel had to be lined with concrete segments. On the British side, these were made at a special plant on the Isle of Grain in North Kent. At its peak, the 8 production lines could produce over 1,000 segments per day. Each one was heavily reinforced with steel bars. The segments varied in weight from 1 to 9 tons and came in up to 268 different shapes. This plant produced in all some 445,000 concrete segments to line the tunnels. The French plant at Sangatte produced a further 252,000 segments in 72 different shapes and sizes to line the tunnels bored by the TBMs working from France. The concrete segments were taken by rail from the Isle of Grain to the construction platform at Shakespeare Cliff. Over 1,200 segments were required each day when the work was at its peak. In all, 1,250 trains were operated by British Rail between these two locations. The trains weighed up to 2,200 tons. Here, a Class 33 diesel brings a train loaded with segments into the sidings at Shakespeare Cliff, which was adjacent to the main Folkestone to Dover railway. The newly arrived segments were stored on site to await delivery to the TBMs. At the busiest phase of the construction work on the tunnels, trains delivered some 7,500 tons of materials to Shakespeare Cliff every 24 hours. On the other side of the channel, segments are lowered down the shaft. Both the rail tunnels and the smaller service tunnel were lined with these concrete segments. On the British side, a ring of segments round the rail tunnels consisted of 8 pieces plus a smaller key segment. The service tunnel had 6 plus the key, and the French rail tunnels needed 5 as well as the key. The equipment to lift and position the segments was an integral part of the TBM. Once they were in the right place, a quick drying grout was injected through the segments to keep them in position. As the TBMs ground through the chalk marl deep under the channel, the spoil from the newly bored tunnels was removed in high-sided wagons. On the British side, the spoil trains deposited their loads onto conveyor belts at the foot of the access tunnel at Shakespeare Cliff. The spoil on the conveyor belts was carried up to the construction platform, where it was loaded onto trucks and dumped into lagoons which had been created behind specially built retaining walls. This extended the construction platform at the site and proved the most environmentally sensitive method of disposing of the millions of tons of chalk marl which the TBMs were excavating as they drove the tunnel onwards. On the French side, the spoil was mixed with water to form slurry, and this was pumped along a 500-metre pipeline to a specially created reservoir at Fontpignon. As with the site at Shakespeare Cliff, this area was landscaped after spoil disposal had been completed. At Fontpignon alone, some 3 million cubic metres of tunnel spoil was disposed of. Meanwhile, deep under the channel, the English and French TBMs were heading straight for each other. As the cutting heads were larger than the line tunnel behind them, neither could reverse. The English machine was steered downwards until it was clear of the line of the tunnel. Here, at its last resting place, it was later entombed in concrete. The French TBM, which completed the tunnel, was dismantled and taken out piece by piece on the construction trains. The first contact between the English and French service tunnels was via a probe drill from the British TBM. At this point, the two TBMs were about 110 metres apart. On the 30th of October 1990, the advancing French TBM met the British probe. The machines have been approaching each other with astonishing accuracy. The difference in their centre lines was just 358 millimetres horizontally and 58 millimetres vertically. On the 1st of December 1990, Philippe Cosette and Graham Fagg demolished the last few centimetres of rock to create the first land route between Britain and the rest of Europe for 12,000 years. Flags and handshakes were exchanged and the celebrations began. The island race could never be completely insular again. With the breakthrough of the service tunnel achieved, work continued on the rail tunnels themselves. On the 22nd of May 1991, the Northern Rail Tunnel broke through, and then at the end of June, the Southern Rail Tunnel was completed. Despite delays early in the construction work, this final breakthrough took place 2 days ahead of schedule. At 2 points under the channel, roughly 1/3 of the way out from each coast, the rail tunnels come together in huge cathedral-like crossover caverns, which enable trains to cross from one tunnel to the other. They also allow one tunnel to be closed off for maintenance purposes at times of low traffic flows. Work on the crossover cavern on the English side was begun from the service tunnel before the rail tunnel TBMs had reached the site. It is located 17 kilometres from the English portal. A TBM later progressed through the cavern, providing unusual and spectacular views of the entire machine, with its long tail of complex machinery behind the cutting head. The Southern Rail Tunnel TBM took 9 days to pass through the cavern. Work continued to complete the excavation of the cavern, which when finished was 163.8 metres long, 21.2 metres wide and 15.4 metres high. When the cavern had been hewn out, massive doors plus the girders and steelwork to support them were installed. These doors are normally kept closed, but are opened when trains need to cross from one tunnel to the other.
When you travel through the tunnel
As if to emphasize the progress of the work, on the 30th of November 1992, a small ceremony took place to mark the Anglo-French land frontier, something which could never have happened but for the construction of the tunnel. Though most travellers will miss it as their trains speed by, these are the plaques which mark the frontier between the two countries. As the building of the tunnels proceeded apace, away from the public view, the massive construction works required to build the two terminals at each end of the tunnel got underway. The two sites were very different. The French terminal at Coquelles, seen here a few miles inland from the coast just outside Calais, is huge. Its 700 hectares make it by far the largest land transport complex in Europe. It has 53 kilometres of railway track and 36 kilometres of roads. The site is low-lying. Bulk infill had to be spread across the site to level and compress it. The earthworks alone here involve the movement of some 11 million cubic metres of material. By contrast, the British terminal at Cheriton on the outskirts of Folkestone, sandwiched between the North Downs and the M20, is much smaller at 140 hectares. The terminals handle the road traffic, cars, trucks, coaches and motorbikes, travelling on Eurotunnel's shuttle services. Through passenger and freight trains cross the terminals on their way between the tunnel and the national rail networks. The white building seen here under construction at Cheriton is the control centre for rail movements throughout the entire Eurotunnel system. Should a fault put this out of commission, a similarly equipped control centre at Calais is immediately switched in to take over. The Cheriton Control Centre is responsible for the operations of both the shuttle and the international services which use the tunnel. Each control centre also handles road movements on its own site. One little-known aspect of the construction phase of the Channel tunnels is the role played by narrow-gauge railways in the work. At its peak, the construction railway was the third largest in Britain. Only British Rail and the London Underground were bigger. The job of the railway was to move both workers and materials to where they were required. Personnel travelled in 3-car man riders. Each of these would carry 90 people, and at the height of the construction work, 1,000 were taken in and out of the tunnels every 8 hours, 24 hours a day. The railway was managed by a controller based underground. In a typical 8-hour shift, he would have to authorise up to 80 separate train movements. This railway was built to a gauge of 900 millimetres. There were double tracks in each of the 3 tunnels, but to complicate matters, trains were often stopped at work sites along the way. There were crossovers at 375-metre intervals, so that through trains could be juggled past those which were stationary. Up to 700 workers were employed on the railway, with a further 300 engaged on maintenance. On the UK side, it took 13 or 14 units to service all the construction sites before the tunnels were joined up. The numbers of personnel required at different places varied on an almost daily basis. Just getting people to their place of work called for an enormous amount of planning. The man riders were powered by diesel engines. At its peak, the narrow gauge railway consisted of some 200 kilometres of track. It has been calculated that over 7 million tonnes of materials were brought into the tunnels, and some 10 million tonnes of chalk marl excavated by the TBMs was brought out. There were 160 locomotives and about 1,000 items of rolling stock. This working is conveying wet concrete in a bullet wagon, so called because of its shape. The hub of the system on the English side of the channel was in the marshalling area under Shakespeare Cliff, the crossroads for much of the railway activity. We saw the spoil wagons earlier in the programme. These constituted about 1/3 of the rolling stock. Much of the rest consisted of these 6-metre-long air-braked flatbed wagons. In addition to bringing out spoil, the other major traffic flows on the construction railway were the concrete segments needed to line the tunnel and the many thousands of kilometres of electric cables and pipes used in fitting it out. The UK narrow gauge railway was in use from April 1988 to April 1993. The total train kilometres travelled during this time was the equivalent of 4.5 trips to the moon and back. On the English side, locomotives and rolling stock were maintained at a specially constructed complex at Shakespeare Cliff. The locos worked off overhead catenary, where this had been installed. They also had batteries to enable them to operate in those parts of the tunnels where the overhead electric catenary had yet to be erected. or in case of a difficulty or an interruption to that power supply. To reach the tunnels from the construction platform at Shakespeare Cliff, all the construction trains had to use one of the 5 tracks in a sloping tunnel known as Adit A2. Because of the steep gradient involved, this stretch was operated using the rack and pinion system, more commonly seen on mountain railways. The pantograph on the locomotive takes power from the overhead supply as the train descends the shaft. Cogwheels under the locomotive engage a toothed rail between the tracks. The rack and pinion system provided the adhesion required for both braking and traction on the 1 in 7 gradient in the Adit. One very special man rider was kept in first-rate order for visiting dignitaries. On this occasion, it is being used to transport the new British ambassador to France to take up his duties. With more of the symbolism which inevitably accompanied this great project, this was the first time in the history of the state that a British ambassador was able to travel all the way to his posting on dry land. Riding with the ambassador, a good idea can be obtained of how busy the construction railway was, with one track occupied with various works trains shunted out of the way for the VIP. A deluxe man rider known to some as the Disney-mobile was equally unofficially renamed the Maggie-mobile in anticipation of a visit by the then Prime Minister for the final breakthrough in December 1990. However, Mrs. Thatcher succumbed to what one might call force majeure in November 1990 and never had the chance to sample the plush blue carpets of this very special vehicle. Once the tunnels had been driven through and the crossover caverns were complete, the next stage in the project was to fit out the tunnels and lay the permanent rail tracks. The floors of the tunnels were made of concrete. Instead of the normal stone ballast used under most railway tracks, the lines through the tunnels were laid on short concrete sleepers known as sonville blocks. These reinforced concrete blocks were fitted with impact absorbing pads and cased in rubber before the track was laid, to give the elasticity which stone ballast normally provides. Some 340,000 sonville blocks were produced at a factory near Sangatte to support the permanent tracks through the tunnels. The track itself consisted of 180-metre long lengths of flat-bottomed rail. This was fed out from rail-mounted gantries using techniques similar to those applied to track laying on conventional railways today. Once in place, the sections were welded together. Because the Sonville blocks did not pass under the width of the tracks like normal sleepers, special spacers were used to maintain the gauge, though the chance of lateral movement was slight in any case, for once they were correctly aligned, the Sonville blocks were set in concrete to lock them in position. The result of all this work is some of the smoothest riding and safest permanent way to be found anywhere in the world. However, the principle of putting supports under the rails and using cross-track spacers to maintain the gauge is not a new one. The engineering logic behind this highly sophisticated track work deep under the channel would have been familiar to Isambard Kingdom Brunel, who devised a similar system using longitudinal timbers to support the rails when he was building the 7-foot gauge tracks of the Great Western Railway from London to Bristol in the 1830s. In addition to the track work, ventilation systems and cables for the overhead power supply for the trains had to be installed through 100 kilometers of tunnels. The catenary, the overhead wires from which the trains drew their electrical power high up in the roof of the tunnel, consisted of 6 separate cables fastened to special supports. For a time, both standard gauge tracks and the 900mm construction railway were in simultaneous use for fitting out different sections of the tunnels. At the French portal, a narrow gauge train conveying pipework waits for clearance to enter the tunnel. To prevent the build-up of heat, each rail tunnel contains 2 cooling pipes, each 400mm in diameter. Water chilled at 2 cooling plants situated near each coast circulates through these. As the fitting out of the tunnels neared completion, Eurotunnel began to reposition itself from being the overseer of the biggest construction project in recorded history to the organization which would have to operate the complex transport system it had created. Traffic consists of the shuttle trains run by Eurotunnel and through international passenger and freight trains, which use the tunnel to link destinations in Britain with others throughout continental Europe. The shuttles carrying cars, coaches and lorries travel through the tunnel and round a turning loop, which leaves them facing the direction they came from, ready for their next trip. The Eurotunnel shuttles carry either cars or trucks. The car shuttles are made up of double-decker wagons for ordinary cars and single-deck wagons for high-sided vehicles. The initial order was for 108 wagons of each type. The double-deck wagons carry 5 vehicles on each deck. The wagons are made of stainless steel and are air-conditioned. They were designed to give the maximum protection against fire. The fireproof doors which divide each wagon are capable of resisting a fire for up to 30 minutes. double-deck wagon is carefully positioned on its bogie. Each car shuttle train is made up of 24 of these wagons, plus 4 loading and unloading wagons. After the shuttle wagons were delivered to the Calais terminal, they underwent an extensive program of testing and commissioning. A freight shuttle wagon arrives at the French terminal by road. The semi-open stainless steel trellis-like design of these wagons was intended to keep their weight down. Each wagon can carry a lorry of up to 44 tons in weight without exceeding the permissible axle loading on the railway. Each freight shuttle train consists of 28 carrier wagons and 4 loading and unloading wagons. On the car-carrying shuttle trains, drivers and passengers remain in the wagons with their vehicles for the journey through the tunnel. On the freight shuttles, the lorry drivers travel in an amenity coach at the front of the shuttle. In these coaches, lorry drivers can enjoy a meal, and they are out of their cabs long enough to make the journey through the Channel Tunnel qualify as one of the regular statutory breaks from driving that the law requires. Eurotunnel's rolling stock requirements were completed by the powerful locomotives which were to haul the shuttles. The design specifications of the locomotives call for machines which could make 10 return journeys each day, hauling up to 2,400 tons at speeds of up to 140 kilometers per hour on gradients as steep as 1 in 90. Each shuttle has 2 locomotives, one at either end. If one fails, the other has enough power to drag the entire shuttle train out of the tunnel. If both fail, the pair on the following train have the capacity to rescue the fail set as well as haul their own train out of the tunnel. This is one of the many test trains operated in the course of commissioning the locomotives. Once the stock had arrived and been thoroughly tested, loading trials began. Trucks run down the ramp at the English terminal and are driven onto a freight shuttle via one of the loading and unloading wagons which are included in each set. A complete freight shuttle train makes for the tunnel. Maintenance of Eurotunnel's fleet is concentrated at the more spacious Calais site. It was here that the 500 vehicles in the initial fleet ordered by Eurotunnel were commissioned and checked before being permitted to enter service. Both routine maintenance and major overhauls are carried out in the workshops at Calais. At last, tunnel is open for business. Let us follow a journey from France to England to see the whole thing working sweetly. Cars drive down the ramps to the platforms and are directed onto the shuttle. The whole process of using these services is designed to be no more complicated than using a motorway where tolls are charged. Cars drive along both decks of the wagons until directed to stop. When each wagon is full, the fireproof doors at the ends are closed. When the shuttle is ready to depart, the outside doors are closed and the powerful locomotives at each end slide into action.
La première est passée, ça referme par deuxième étape.
Once in the tunnel, speeds build up until the normal operating speed of 130 kilometers per hour is reached. Passengers may leave their cars to stretch their legs if they wish. The entire journey takes only about 35 minutes. And soon the train is drawing to a halt at the platform at the English terminal. The internal and external doors are opened and the drivers prepare to move off. It all seems so simple. How did we ever manage without it? The Channel Tunnel is now up and running, and in the course of this programme we have seen something of the enormous effort which has gone into turning this centuries-old dream into a reality. The heart of the tunnel system is to be found in the control room at Folkestone. There are no fixed signals in the tunnel. Trains are controlled with a state-of-the-art cab signalling system. This is probably the most sophisticated signal box in Europe. It controls not just the shuttle trains, but through freights and the international passenger trains which use the tunnel, the Eurostars. The through international passenger trains, which run between London, Lille, Paris and Brussels, are operated jointly by the British concern Eurostar in association with the national railway companies of France and Belgium. The Eurostar sets consist of 18 coaches and 2 power cars and can carry some 770 passengers. At nearly 400 metres long, they are by some way the longest passenger trains running on British tracks. Their technical specifications owe much to the famous French trains à grande vitesse, the TGVs. Adjacent to the domestic station at Waterloo, a brand new international terminal forms London's Eurostar gateway to mainland Europe. The ambience here owes more to air travel than traditional railway practice. This is no accident, for the high-speed city centre to city centre service offered by these trains competes directly and successfully with the airlines on their routes from London to Paris and Brussels. An impressive array of 5 Eurostars lines up at Waterloo International Terminal. On the platforms, members of staff prepare to greet passengers as they board their train. One of the sets glides out of the station to begin its journey through South London and Kent to reach the Channel Tunnel at Folkestone, through which it will progress towards its destination on the continent. On-board catering services are of the highest order. Bad jokes about the much-abused British Railways sandwich certainly do not apply on these services. The Eurostars have to be able to pick up current at 750 volts DC from the third rail system of electrification used in the south of England and from the two different overhead systems used in France and Belgium. There is no dedicated high-speed line through Kent at the moment, and although existing lines have been upgraded, the limitations of the third rail system restricts the speed of the Eurostars on the English leg of their journeys, though they do make an impressive sight as they purr through the lush garden of England. Once out of the tunnel and into France, they can really stretch their legs and travel at speeds of up to 300 kilometers per hour on the high-speed line from the French portal of the tunnel to Paris. When the high-speed line from the English portal of the tunnel to London is built, we can look forward to these sort of speeds on the UK side of the channel, and journey times from London to Paris and Brussels will be even better than those which pertain today. These are undoubtedly the trains, and this is the railway of the new millennium. It is no exaggeration to herald these trains as the precursors of a new golden age for the railways. The French terminus of the Eurostars is Gare du Nord, in the heart of Paris. And the trains also serve Brussels, the administrative capital of the European Union. Few would have thought that all of this would have been possible less than 20 years ago, but now it is a reality, thanks to that remarkable expression of man's determination and ingenuity, the Channel Tunnel.